Dark matter is a hypothetical kind of matter that cannot be seen with telescopes but accounts for most of the matter in the universe. The existence and properties of dark matter inferred from its gravitational effects on visible matter, on radiation, and on the large-scale structure of the universe. Dark matter has not been detected directly, making it one of the greatest mysteries in modern astrophysics. Dark matter neither emits nor absorbs light or any other electromagnetic radiation at any significant level. According to the Planck mission team, and based on the Standard Model of Cosmology, the total mass energy of the known universe contains 4.9% ordinary matter, 26.8% dark matter and 68.3% dark energy. Thus, dark matter is estimated to constitute 84.5% of the total matter in the universe, while dark energy plus dark matter constitute 95.1% of the total mass energy content of the universe. Astrophysicists hypothesize the existence of dark matter to account for discrepancies between the mass of large astronomical objects determined from the gravitational effects, and the masses calculated from the observable matter that they can be seen to contain. The gravitational effects suggest that their masses are much greater than the observable matter survey suggests. Dark matter was postulated by Jan Oort in 1932, albeit based upon insufficient evidence to account for the orbital velocities of stars in the Milky Way. In 1933, Fritz Zwicky was the first to use the virial theorem to infer the existence of unseen matter, which he referred to as Dunkel Materie, dark matter. More robust evidence from galaxy rotation curves was discovered by Horace W. Babcock in 1939, but was not attributed to dark matter. The first hypothesis to postulate dark matter, based upon robust evidence, was formulated by Vera Rubin and Kent Ford in the 1960s-1970s, using galaxy rotation curves. Subsequently, many other observations have indicated the presence of dark matter in the universe, including gravitational lensing of background objects by galaxy clusters such as the Bullock cluster, the temperature distribution of hot gas in galaxies and clusters of galaxies, and, more recently, the pattern of anisotropies in the cosmic microwave background. According to consensus among cosmologists, dark matter is composed primarily of a not yet characterized type of subatomic particle. The search for this particle, by a variety of means, is one of the major efforts in particle physics today. Although the existence of dark matter is generally accepted by the mainstream scientific community, some alternative theories of gravity have been proposed, such as Mond and Tevez, which try to account for the anomalous observations without requiring additional matter. However, these theories cannot account for the properties of galaxy clusters. Overview. Dark matter's existence is inferred from gravitational effects on visible matter and gravitational lensing of background radiation, and was originally hypothesized to account for discrepancies between calculations of the mass of galaxies, clusters of galaxies and the entire universe made through dynamical and general relativistic means, and calculations based on the mass of the visible, luminous matter these objects contain, stars and the gas and dust of the interstellar and intergalactic medium. The most widely accepted explanation for these phenomena is that dark matter exists and that it is most probably composed of weakly interacting, massive particles that interact only through gravity and the weak force. Alternative explanations have been proposed, and there is not yet sufficient experimental evidence to determine whether any of them are correct. Many experiments to detect proposed dark matter particles through non-gravitational means are underway. One other theory suggests the existence of a hidden valley, a parallel world made of dark matter having very little in common with matter we know, and that could only interact with our visible universe through gravity. According to observations of structures larger than star systems, as well as Big Bang cosmology interpreted under the Friedmann equations and the Friedmann-Limiter-Robertson-Walker metric, Dark matter accounts for 26.8% of the mass-energy content of the observable universe. In comparison, ordinary matter accounts for only 4.9% of the mass-energy content of the observable universe, with the remainder being attributable to dark energy. From these figures, matter accounts for 31.7% of the mass-energy content of the universe, and 84.5% of the matter is dark matter. Dark matter plays a central role in state-of-the-art modeling of cosmic structure formation and galaxy formation and evolution, and has measurable effects on the anisotropies observed in the cosmic microwave background. All these lines of evidence suggest that galaxies, clusters of galaxies, and the universe as a whole contain far more matter than that which is easily visible with electromagnetic radiation. Though the theory of dark matter remains the most widely accepted theory to explain the anomalies in observed galactic rotation, some alternative theoretical approaches have been developed which broadly fall into the categories of modified gravitational laws and quantum gravitational laws. Baryonic and non-baryonic dark matter. There are three separate lines of evidence that suggest the majority of dark matter is not made of baryons. The theory of Big Bang nucleosynthesis, which predicts the observed abundance of the chemical elements, predicts that baryonic matter accounts for around 4 to 5% of the critical density of the universe. In contrast, evidence from large-scale structure and other observations indicates that the total matter density is about 30% of the critical density. Large astronomical searches for gravitational microlensing, including the Macho, Eros and Ogle projects, have shown that only a small fraction of the dark matter in the Milky Way can be hiding in dark, compact objects. The excluded range covers objects above half the Earth's mass up to 30 solar masses, excluding nearly all the plausible candidates. Detailed analysis of the small irregularities in the cosmic microwave background observed by WMAP and Planck shows that around 5/6 of the total matter is in a form which does not interact significantly with ordinary matter or photons except through gravitational effects. A small proportion of dark matter may be baryonic dark matter. Astronomical bodies, such as massive compact halo objects, which are composed of ordinary matter but emit little or no electromagnetic radiation. The study of nucleosynthesis in the Big Bang gives an upper bound on the amount of baryonic matter in the universe, which indicates that the vast majority of dark matter in the universe cannot be baryons, and thus does not form atoms. It also cannot interact with ordinary matter via electromagnetic forces. In particular, dark matter particles do not carry any electric charge. Candidates for non-baryonic dark matter are hypothetical particles such as axions, or supersymmetric particles. Neutrinos can only form a small fraction of the dark matter, due to limits from large-scale structure and high-redshift galaxies. Unlike baryonic dark matter, non-baryonic dark matter does not contribute to the formation of the elements in the early universe, and so its presence is revealed only via its gravitational attraction. In addition, if the particles of which it is composed are supersymmetric, they can undergo annihilation interactions with themselves, possibly resulting in observable byproducts such as gamma rays and neutrinos. Non-baryonic dark matter is classified in terms of the mass of the particle that is assumed to make it up, or the typical velocity dispersion of those particles. There are three prominent hypotheses on non-baryonic dark matter, called cold dark matter, warm dark matter, and hot dark matter. Some combination of these is also possible. The most widely discussed models for non-baryonic dark matter are based on the cold dark matter hypothesis, and the corresponding particle is most commonly assumed to be a weakly interacting massive particle. Hot dark matter may include neutrinos, but observations imply that only a small fraction of dark matter can be hot. Cold dark matter leads to a bottom-up formation of structure in the universe, while hot dark matter would result in a top-down formation scenario. Since the late 1990s, The latter has been ruled out by observations of high redshift galaxies such as the Hubble Ultra Deep Field.